Um, so, okay, maybe we can just start. Hello, everybody. A warm welcome to this webinar series on application of machine learning in oil and gas industries, that is the energy industry. On the behalf of SP Arkin University, we would like to welcome Divyanshu Vyas. Thank you very much for being here. So a little bit about Divyanshu. He did his bachelor's degree in petroleum engineering from Pandit Deen Dayal Energy University. It is one of the very good universities in India for petroleum engineering. After that, he did his master's in Indian Institute of Technology, ISM Dhanbad. Again, this is the best institute for petroleum engineering in India. And he has his minor in artificial intelligence and machine learning for geosciences. In 2020, he has given an national exam and he got an all India rank of 17. And talking about his professional career, he worked at many places. The most important ones standing out are he worked at Larsen and Toubro Infotech Limited for 2 years, like for 1 year as a subsurface data analyst, and currently he works in Accenture as a data scientist. He's also the founder of Petroleum from Scratch, uh, which mentors the oil and gas community on Python, machine learning, and relevant concepts for the domain. So, and he has a very vast experience on petroleum data analytics. So we hand the present, like Divyanshu would be presenting his presentation, and thank you very much for now. If anybody would have any doubts, please wait till the end of the presentation and you can ask all of those doubts at the end. Thank you.
Thank you very much. Thank you for introducing. Thank you for inviting me. And thanks everyone for taking time out to attend this session. We're going to talk about the road towards, why and how to get started with energy or petroleum data analytics, assuming that the crowd over here, you are trying to begin your journey in here and you just want a pathway or something like that, and kind of projects that can be done, and the kind of projects that I have done in my experience till date in this journey. And we'll look at a few examples from the upstream sector, the downstream sector, a few generic examples that can help the energy industry as a whole. And then we will try to look at a workflow of how machine learning and data science can help generate value. And then we will open the floor up for questions. So by the end of this session, if you are not familiar and I try to make sure in each and every of my session, I try to make sure that my language is very understandable and closer to the students. So that will be something that will help you gain better hands-on exposure, and not just big words or terminologies, and you won't be lost in this presentation. You will feel like you can do it. That's something that we always want when we attend any session. So even if you know nothing about machine learning and data science, after this presentation that I'll be sharing today, you will have a clear picture in front of you. You will have a workflow in front of you, and you will be like, okay, I can go back now and I can start my journey and I can do these things and I can do good. So let's start with this motivation, and let's talk for about let's say 45 minutes to 1 hour, and then we will maybe end this session with a few questions. So I'll share my screen and let me know once it is visible. Can you see my screen?
Yes. It was, yes.
Okay, perfect. All right. So yeah. So the topic is Introduction to Data Science and Machine Learning for the Oil and Energy Industry. And let's get started with the motivation behind it. Of course, the reason that oil and gas industry is thriving these days in terms of data science, and the energy industry is thriving these days in terms of data sciences, because of two reasons, basically. One is the huge loads of data, they have been accumulated over decades and decades, but they were not being used to generate any value. They were just being lying around there, and people were using old technologies, old formulas, for example, old correlations. You'll see that most of the petroleum softwares, uh, they are somewhere using the old correlations, empirical correlations that are based on God knows what, right? And it might work for some areas, but who knows how it can work for other areas as well. So that's something that that's a big question mark, because we are not using data, we are using the things that are already there. So that's one thing. How about you generate your own value from your own data? So that's the first benefit that you can generate from, right? For example, I'll try to give an example of a doctor. If you go to a doctor, your doctor does not, does not treat you uh, based on, someone else, right? Your doctor treats you as your own situation. Your doctor treats you based on your own data. He won't be like, hey, he won't use a kid's data to treat a 25-year-old person, right? He would, in fact, even if not your data, he would try to look for people around your age and around your demographics and around your health conditions to judge you, right? So your doctor always focuses on how you behave and how your body is behaving, and then takes that data and generates value. And that's why doctors normally they treat you so well. Just imagine if there in the doctor's books there were correlations written based on someone who was no way connected to your kind of health, and your doctor is suggesting you pills based on those kind of people. Would you be able to recover from whatever you are trying to recover? Absolutely not, because your doctor is using data which is not connected to your body, right? So that's something which is happening in many industries today, and we need to come to the data driven formulations, because if you are using correlations which do not match your current reservoir or your current equipment, you cannot expect good results. So that's one thing that data science can bring in, right? So that's one thing. And as we go on, and if someone is from the upstream industry, I mean, the great thing is these days computational power is increasing. You can see there are cloud-based technologies available for computation. You are having Azure and Amazon Web Services, AWS, and Google Cloud Platform, and all these giant players. They're trying to help you provide high computation so that your latency it reduces, right? So if you build a software which takes in data, generates some machine learning model on it, and generates results out of it, these cloud softwares make that process so fast that you won't even realize that you have processed terabytes of data in just about a minute. So with the introduction of all these things, and with the value that a data driven industry can generate, it's high about time that we can now look into this. And being from the oil and energy industry, I would like to motivate that this industry has been very slow to adapt to data sciences, right? And that's a motivation in itself, because if you were, for example, if you are from the healthcare industry, AI has been running in the healthcare industry for quite some time now. So if you want to get in there, it's like it's a good competition. But in oil and gas, at our level, at a master's or grad student level, or even like in that age group, if you develop some sort of exposure towards machine learning, solve some critical problems of the industry, and you also have a great domain knowledge, you will not find anyone close to you in that age group. People are there in the research ages and all, but younger data scientists plus petroleum engineers are hard to find. So that's a good thing that makes people more and more hireable as soon as they complete their bachelor's and masters and all. So it's a great hiring opportunity as well. For it's a great way to get hired. And for those who are highly enthusiastic about mathematics like myself, it's a great thing to learn, even if you are not from oil and gas. So that's the motivation and the introduction, right? Moving on. These are a few examples where I would not use the previous correlations which are given to me by the various 50-year-old scientists. Rather, I would use the correlation that my data is suggesting, right? That's why I would say that data-driven methodologies can help generate value. So this is a use case example from a field that I was working on, like the data from a field that I was working on. And of course, there are various equations or correlations given for geothermal gradient, like temperature as a function of depth, as well as API gravity, which is kind of a reciprocal of specific gravity of oil that you see in the right corner, versus viscosity. Everyone knows that higher the viscosity of oil, it intuitively feels like the viscosity leads to a higher specific gravity as well, which kind of reduces the API gravity, because API gravity is inversely proportional, right? So there are correlations that specify the relation between API gravity and viscosity. So I had two options. I could have used those correlations, or I could have looked into the data that I have from the current field and ignore those correlations. And when I took the data from the field that I was working on, first looking at temperature versus depth, you can see a great linear trend, direct proportionality trend that I could see. The same thing could be observed for API gravity versus log of viscosity, which again tells me that, hey, there is a sense of pattern that this field is following. So would you take in the old correlation, which was written 50, 60 years old, or maybe 100 of years back, or would you use the data-driven correlation from the existing field? I would use the later on, because I know this field I'm working on. If this field is suggesting some kind of relation, I would rather use that, because the solution I'm building is for this particular field. I'm not using the solution for other fields. So this is where data-driven solutions come into the picture. And this is kind of what machine learning also focuses on. The data that you have, assume nothing from the past. The data that you have, you use that to generate something. And you use, every field has its own solution, a unique correlation. That's what data science and machine learning is all about, right? And this is done in Python. So the tool that we use to do something like this is basically Python. And this can be a standalone machine learning model in itself. If you're trying to generate a regression model between API gravity and viscosity, why not build this for a particular field itself? And when you move to the next field, build a new model for that field. And when you move to the third field, build a new model for that field. Because the computation is so fast, a newer model would not hurt you with time that much. But if you use an old correlation, it might hurt you with inaccuracies. Okay, moving on. So why machine learning? Of course, I mean, a data science workflow, which I will just show you in this presentation. Data science workflow has a lot of things, but at the very end of it, your aim is to generate a machine learning model, right? Not always, but normally people want to build a machine learning model, just like I introduced here, right? Why machine learning? Let's go through the points that I've written. Most engineering workflows, they assume physics of some sort, which involves a lot of assumptions itself, which is very understandable. You see anything, it's based on assumptions. Assume this is a sphere, assume this is a square, assume this is homogeneous reservoir, something like that. So that's at the very beginning, you are creating an inaccuracy, right? So that's the first problem with the traditional workflows. For example, Darcy's law is valid, but it is valid only under a few assumptions, right? So we are missing that part, because that's like a condition supply kind of thing. You see the product's advertisement, but do you always see the conditions apply caution at the bottom? People normally forget that, right? So that's something that we have to look into, because that's going to generate, because when millions of dollars are at stake, you need to look at these inaccuracies. 𝐴RP's laws, which is a traditional decline curve analysis model, which helps you generate oil production forecasts. These equations, these models, they are valid, but only as long the strong assumption for decline curve analysis is that oil production conditions, they must remain consistent, which is the same for every physics-based solution. Your conditions, they must remain consistent for the solution, the physics-based equation to be followed. As soon as the conditions they break, your model will stop giving accurate results. Would you rather want that model or some robust model that will adapt to the changes in your data? So these are a few examples where we can bring something new. Hence, we need a robust machine learning technique, a robust technique that assumes no physics, and it starts building its brain from scratch. When you create a machine learning model based on the data, of course, the data that you receive, it has a lot of processing to be done to it. It has a lot of furnishing to be done to it. That's data science part. But once you have made the data ready for use, you can then use it for building a machine learning model. The good thing about machine learning is it never assumes anything. It builds its brain from scratch. Focus on this very important line. It builds its brain from scratch. Can I use? It builds its brain from scratch. Okay, it's a very important thing. And that's the doctor example that I gave you. Every new patient is it's a new model that you are trying to build, right? So always remember, machine learning assumes no physics. That's the biggest example. That's the biggest win for machine learning in oil and gas industry. But I'll try to throw a word of caution here. These days, I mean, not blind machine learning can help. I mean, sometimes you need physics to guide you through. So there are popular hybrid models as well, which use the best of both the worlds. We cannot just discard that, hey, Darcy's was totally incorrect, right? He might have done something good, right? Then that's why the books are publishing his solution. So these days, scientists, what they are trying to do is they're trying to build a lot of industries, a lot of companies in our industry, they are building hybrid solutions, which is like 70-30 fraction, 70% data-driven solution plus 30% weight given to physics-based solution. And the combination of both, that is the final solution. So if you're trying to forecast oil production, use 70% weight from machine learning forecast, 30% weight from what decline curve analysis is suggesting, and then combine and then use it. So that even if machine learning was in error, physics might help. Even if physics was at error, machine learning might help. So we have to be realistic in what kind of solution is helping our case. So machine learning is a technique using which we can teach the computer some rules, some physics purely based on the data, right? This is a layman definition for what machine learning is. Machine learning is a technique using which we can teach the computer some rules, some physics purely based on data. And just because it is purely based on data, right? We might need a lot of it. We might need a lot of data, good quality data, in order to build a good quality model. And there is the challenge itself. Oil and gas industry, I mean, right when you start learning data science for oil and gas, you have to realize that not all kind of data would be available to you, right? So to train yourself on such examples is a challenge, and then to go into the industry and then realize that the data that you were working on while learning was totally different, that's again a challenge. So because it is data driven, the quality of the data like help it impacts your solution a lot. That's why the hybrid models are winning these days. But assuming that we have good quality data and good quality machine learning models, we can say that once it learns, it can produce its own forecast, results, predictions in no time, given the computation power is high. And it is a way to automate a lot of workflows. Okay. So a lot of good examples, a lot of good values are generated. I mean, the team that I've been working with, they have been generating a lot of revenue for actual public, actual community by providing them with machine learning and data-driven solutions. Be it any industry, be it mining industry, be it the electric vehicle industry, be it oil and gas, typical oil and gas hardware industry, be it downstream industry, pipelines, whatever. Every industry is gaining a lot from data science. And I've seen it. I've been lucky enough to see it generating value, right? Moving on. Let's now talk about the applications of and the workflow of what data science is, right? So you first start with data collection. Okay, you first start with data collection, and remember, if you are working in an industry, if you are working in a company, XYZ, whatever company that is, and you are looking forward to creating a machine learning solution in the future, you have to start planning about it right now, because data collection has to happen for the solution you are trying to generate. So suppose I want to predict pipeline corrosion in the future, I need to collect data from the history about, or maybe from now for 10 years, I need to collect cases for all kind of pipeline failures and normal evidences. I need to collect data for them so that I can use these 10 years of data into a machine learning model. Most of these industries, they are not doing that. Most of these companies are not doing that. And you cannot just plug and play, right? You have no data. You cannot ask that, hey, I don't have any data. Can you do some machine learning? No, no, sir, we cannot. So you have to ask them that, hey, do you have the last 10 years of data for the solution you want me to build? If they say no, then you blame them on them, right? That you have not collected the data. How can you bring the machine learning solution to it? So data collection is the first step, right? Sensors, etc. All of these things are installed in oil and gas, thankfully. And we are lucky enough for that. There is a sensor to record bottom hole pressure. There is a sensor to record surface pressure. There are flow meters located. Offshore also, there are a lot of sensors located. So all these sensors, IoT devices, they help you generate, help you record data for a lot of time and a lot of frequency. So that's good. Okay, data collection is happening. So first step is to collect that data and bring that data into your solution, right? So you bring the data and then you have to process it. Data pre-processing has to happen, right? Data pre-processing has to happen because the data that you have collected might have a lot of errors in it. The data that is coming from the sensors, it might have a lot of noise on it, right? So for example, if it was an oil production data, right? You are collecting oil production data, because you are collecting it from somewhere, it might be looking like this. It might be looking like this. But the original trend might be this thing. The original trend might be this green thing, right? So you might have to cover up for all this noise, right? If you can see the annotations that I'm creating. So this noise, all that noise that you have, all these fluctuations that you have, you might have to process all these fluctuations. And that's a very important part. That's called data pre-processing. So for all that's where domain knowledge comes in. That's where petroleum or energy knowledge comes in. If, for example, there is a porosity column that you have in your data, you have to first look at the distribution of that column. You have to visualize that column using Python or whatever. And you have to look at, hey, for example, suppose I know in my reservoir engineering classes, I read that 47.6% is the theoretically maximum porosity that I can see. But if my porosity column is showing 60% porosity, I need to check for that, right? So that goes under data pre-processing. There might be a case where you might have to combine two or more columns to create a singular column. For example, you have population of a city, and you also have area of that city. Population and area separately, they don't make sense, but population divided by area, which is population density, that makes sense. Because population density can tell you more about a city than population single-handedly can. That tells you how closely people are located, how congested that city is, and that can tell you that what kind of pollution that city can expect or something like that. So you might have to look at the problem statement, and you might have to do some processing to the data. So this is the data science part of it. Okay, this is the data science part of it. So that's the second step. Data collected, and then you clean that data, process that data. There might be errors in that data. Some numeric columns, they might have inverted commas located in them. A lot of random problems might be there in your data. So you might have to check for that. Then feature engineering, like I told you, feature is nothing but a column. Every column is called a feature in data science. So features, you might have to correct for the features. You might have to change the features. You might have to change the units of a feature. That is also feature engineering, right? For example, you see that something is in something that should be in the scale of micrometers is in scale of kilometers. So you might have to divide it by, let's say, multiply it by according numbers, and you have to convert that to a better number. You might have to scale the numbers to 0:1 ratio. For example, effective permeability does not make sense when you have multiple reservoirs in your data. Relative permeability might make sense because that helps you compare one reservoir to the other. So you might have to divide every effective permeability by its corresponding absolute permeability to generate a column called relative permeability. So that's an example of petroleum engineering, feature engineering, right? So all of these things I'm doing to the same data set that I first received as the very raw data. Okay. And finally, we need to do the last 3 steps. Finally, we can generate some conclusions about the data by visualizing it that, hey, this is my inference about this data. When I visualize it, I again generate some inference. So visualization and inference, they are like a loop. You infer something, you visualize something. You might have to go back to processing the data again. Once you visualize that, hey, there is some error to it, you have to go back and process it again. And you come back and you visualize and you see that, hey, my error is now corrected. Now I can go forward. Finally, once you are very happy with your entire data set up to this step, from step 1 up to step 5, you have taken the data, you have cleaned it, you have processed it, you have fabricated it, you have done some feature engineering, you have checked for proof, you have checked for concepts, you have checked for everything, you have visualized it, you have generated inferences that, hey, I was assuming that this would be the case because this is an unconsolidated rock. I was assuming that my porosity would be huge. And that's what I'm seeing in the visualization. So all of these assumptions you need to check first. Make sure what you were thinking is actually conveyed by the data. Finally, when that is the case, you go to the machine learning solution. Okay. So like I said, the first, let me use a different color. The first, this much steps, these steps, they take like 90% of your time in your data science workflow. 90% of your time in a data science workflow. Machine learning is like the cherry on the cake. You cannot do data science if you don't know first 5 steps. All you know is machine learning. I've seen a lot of students, they would do computer vision and all these sorts of fancy things, but they don't know random Python, processing steps. And that's not a good way to go about it. So don't just rush towards machine learning is what I would like to recommend whenever you start your journey. Okay. So all the programming language you'll be using would be mostly Python or R, right? So if I tell you what kind of language you'll be using for, let's say, first 3 steps, what kind of package you would be using for first 3 steps, it would be pandas. In Python, there is a package called pandas. Sorry for my handwriting. I'm using my mouse, forgot my pen. So pandas is the package that I'll be using for data related stuff. It's like the Microsoft Excel of Python. Okay. You can do all kind of tabular computations with pandas. Okay. Deriving inferences and visualizations, they can be done by matplotlib. I'll use the short term MPL, matplotlib. It's a MATLAB style plotting library of Python. Okay. So visualization in Python can be done using matplotlib, and in pandas, you can do a lot of data related processing steps. And finally, machine learning can be done in Python using sklearn. sklearn. I'm using short forms because I don't have a pen. Okay. So these are the random connections to the Python programming language for the various steps in your data science workflow. For those who did not know, of course. Let's now move to the right-hand side of the presentation. So I've given some examples that you can do in oil and gas or energy industry, and I'll add a few more to this example list. One is mineralogy identification. So suppose you have a thin section image data from various rocks. If you are a geologist, you might know better. For various samples collected from a particular field, you have thin section images. You can use computer vision, image processing, and machine learning combined to generate a machine learning model that just takes in the input, and then it results an output where it circles various sections of the thin section image, and it says that, hey, this is let's say this is quartz, or this is feldspar, or whatever, right? Something like that, which can help you generate a lot of inference about the kind of rock you are dealing with. I'm not from geology background, but I know the machine learning solution that runs to do it, right? I'm not sure about the value that it helps generate, but this is a good example that I have seen being researched upon. So mineralogy identification is a good example. EOR screening is again a good example where you can, take in the rock properties and the oil properties and suggest what kind of enhanced oil recovery technique can be a good fit for this kind of reservoir. So suppose your oil viscosity is very low and your depth of the reservoir is kind of high. Your machine learning model would suggest that, hey, why not use miscible EOR, right? Because that's what can be very good when your depth is so high, because miscibility can be attained, right? So that's EOR screening for you. Pipeline corrosion identification. That's a great impact generating product that machine learning can bring. Suppose you have pipelines that are lying thousands of feet below the surface of an offshore system, and you have a machine learning model that suggests that, hey, 10 or let's say 5 hours from now, something wrong is going to happen in your pipeline at this particular location. That's pipeline corrosion identification. It's an image processing based solution that can look at the current image, the live image. All you have to do is install cameras at the bottom. You don't have to invest too much into ROVs or something. You have to install cameras at the bottom, and you don't have to it's like total eradication of human interference. You just feed live images to the machine learning solution, and that machine learning solution tells you that, hey, I think something's going wrong in the next five hours or something. So you can accordingly prevent that from happening. Even if the suggestion was incorrect, even if the suggestion was only 70% accurate, you still are being safe, right? So that's a good impact that this can generate. Oil production forecasting is again a good example, because you can forecast how much oil will be produced in the next 2 months, and you can see how much reserves are left in your reservoir. It is currently done using reservoir simulation softwares, but like I said, they are having a lot of uncertainties, a lot of accuracies, and a lot of the speed slows down because of the number of grids that there are. So that's gaining more and more popularity, something that I've also worked on, production forecasting, and some other kinds of solutions that you can, the list keeps on growing. Okay, moving on. So a typical data science and machine learning workflow, you have a raw data set. It can be comma separated file format, Excel sheet or whatever. You bring in, you apply some sort of, this is, so you can see this is a good example that I have actually worked on. So you can see, I realized that a lot of my section of the data was empty. Null values were there. And would you remove these columns just because 2-3 rows are missing out? Of course not. You might have to do some interpolation or, uh, random like trend based fitting or something like that to fill in. You have to fill in for NaN. In Python, when you see these rows, they'll say that there is a nan in it. So it's a Python's way of telling you that, hey, there are missing values in it. So you have to convert the data that looks like this. So this is a heat map. So everything is a column on the, it's like these are the columns and these are the rows. Okay, these are the rows, and I'm like looking at my data and coloring accordingly. If the value is there in the row, I would color it as black. If the value is missing, I would color it opposite to black, which is white. So you can see there are a lot of white spots in my data set, which says that a lot of missing values are there in my data set. So you can see I need to apply something, some data processing step to fill in, and you can see finally my data looks completely filled. And then more of these kind of things will be applied to your data. So this is just one problem that I'm suggesting, but your data normally has a lot of problems. You might see that in the data that you have, you might have some problems at this particular cell, some problem at this cell, some problem at this cell. So it might take a lot of your time. You might have to spend 10 hours, 20 hours, maybe sometimes 2-3 months are gone to just process and clean the data. Once the data is clean, you can then visualize a few things. So for example, here you can see this is me looking at carbonate porosity and sandstone porosity distributions. And intuitively, I know that carbonate porosity distribution would be centered around a lesser value as compared to sandstone. You can see the central median, because this is symmetric, the average sandstone porosity is 20 and the average carbonate porosity is 10, which is a good thing, right? So that's something that I already knew, and now I can infer from the data also. So this is where domain comes in with data. What your domain is suggesting is in your brain, but then you see that the data is also suggesting the same thing. Then you are happy. Then you are like, okay, now I'm getting to the right direction. Okay. Again, when I plot porosity and permeability, correlations, you can see sandstone is having a low slope, the blue line, and carbonates are having a kind of a high slope, but both are linearly increasing as porosity is increasing. Permeability is also increasing, but you can see there are some outliers as well, which of course can be fractured examples or something like that. So of course, I mean, there will be some trend breakers always, but you can see that what you are feeling in your brain based on your petroleum knowledge, you can see from the data. So assuming by this step, you have covered all the fundamentals of data cleaning, data processing, feature engineering, and whatnot, you have a data which is now ready to be put into a modeling phase. You can use machine learning, and to do machine learning you have to decide what is your target variable. For example, if I wanted to predict permeability of a reservoir using other rock parameters which are going to be my x, you have to split x and y first. Y is my, let's say, permeability. X is my, let's say, it can be porosity, it can be single parameter, or it can be multiple parameters. So suppose this much part of my data is x and one column of my data is y. Okay. So I have to make that decision first, and then I can feed that x and y into a mapping algorithm, which is machine learning model. It can be a linear regression model. It can be a deep learning artificial neural network model, which can be a topic for some other day. But whatever is happening, all is happening is this mapping between x and y, right? This mapping between x and y, which a correlation was also telling you that, hey, porosity permeability equals to 0.579 times of porosity to the power 4.4. That's my correlation, but I have built this correlation on a field in North Sea. If you are working on Bardmer field, I'm not sure how that correlation will work out. So that's when the word of caution brings machine learning to it. Why not? If I have 2 lakh rows of porosity permeability data, I can feed that into a machine learning algorithm and I can generate the x and y correlation by machine learning. And finally, this sort of equation can be found out that, hey, y equals to mx plus c and something like that. And finally, you can use that model to generate permeability for any new porosity that you find. Okay. Or this is just a random example, but you can have your own use case. So this is an entire workflow of data science and finally machine learning. Okay. So just an introduction about what kind of machine learning methods that you can see. Okay. So there is two kind of families, okay, split by this particular line. There can be, you know, these are forecasting methods, I think. Yeah, this is a combination of both. Okay. So you can see machine learning is supervised learning as well as unsupervised learning. Supervised learning is when in the data set itself, you have both X and Y, but there are some cases where you don't have the Y, you only have the X, something like a clustering solution and all, which is very rarely used, but there are those examples. But the focus is always on supervised learning, which I just showed you here. In this case, you have Y, right? So this is supervised. But if you only had X, that would be unsupervised. Okay. Okay, so artificial intelligence, machine learning comes as a subset of it. Okay, there can be various methods like for time series forecasting, supervised learning, unsupervised learning. There can be deep learning methodologies as well, which is based on a different kind of mathematics, which is based on artificial neural networks, right? So for forecasting, there can be models like ARIMA, and this is a circle that I have created just for forecasting enthusiasts, right? In supervised, you can have regression, you can have classification. I'll give you an example of what regression, for example, if you want to predict the temperature of a particular system using all the other parameters, that's regression because it's a continuous parameter you're trying to predict. But if you wanted to predict what kind of lithology that a particular reservoir has, whether it's a sandstone or a carbonate or whatever, based on rock and other properties of that particular field, that's a classification project. You have an image, you want to classify whether it's a cat or a dog, that's a classification project. You have a lot of properties from your city, you want to predict what will be the price of the house, that's a regression problem, right? So whenever you have the body parameters of a person, you want to predict its his or her blood pressure, that's a regression problem because you are trying to predict a continuous parameter. But you have the body parameters, you want to predict whether that person is a male or a female, not looking at that person, just looking at the biological parameters. You can call that a classification problem, right? So all these are a high level understanding of what kind of machine learning algorithms are there, right? So this is again the same project that I was showing here. This is again that same project, but it's like a zoom in of that project. Okay. So what I did here is I had this correlation from a book called 𝐷𝐴, okay, between porosity and permeability. This is something that I use extensively when I do classes, when I try to motivate students into following machine learning. Okay. This is something that I did to motivate myself. Okay. What I did was I took a correlation and I generated the data from this correlation. Okay. So you can see that this is the correlation which were taken as input porosity, coordinate water saturation, and permeability. For those who are not familiar, if there are people who are not familiar, just ignore. It's like x1, x2, and y. Okay. And I've generated my own data from this particular correlation itself. Now, I'm not showing this correlation to the machine. I'm not giving the machine this correlation. I have this data, just like any data science problem would have. You would have data, right? And then you would feed that. This is just visualizations, nothing else. Then what I would do is I would feed this data that I've created, I would feed it to a machine learning model in Python. So this is how you do it in Python. I'm using a decision tree regressor or any algorithm. I've also worked on the same problem. I've used various like random forest regressor also, can use artificial neural network also. But like I said, not today's topic. So finally, once I give all these, all the data points, let's say not all these data points, but I gave only, let's say a part of this data, 80% of the data. So if my data had 100 rows, I would give only 80 rows of the data to my machine learning model. I took, let's say 70,000, I remember. So some part of the data, 80% or majority of the data I passed on to the training phase. This is called machine learning training. Okay. This is called training. Once I train the machine learning model, okay, and during training, you can see that initially the error was huge, but as I trained on more and more examples, you can see the error was going down, which was a good thing. Finally, once I did that, I predicted. You can see this is model predictions. Okay, this is model predictions. I took the unseen part of my data, which is called the test data set, and I predicted my permeability on that part of the data. Okay. And you can see 3.74 was my prediction for the first example. And then I also printed the actual case, actual correct answer for that. You can see 3.74 is the actual answer. Which means what? Which means that if I provide enough data for the computer to learn from, the computer can learn the correlation that it had no idea about. Because finally, you can see these 5 examples, all of them are matching with the exact actual answers. Can I finally conclude that the machine, if provided good enough data, the machine can correctly identify? Because this is unseen data that the model is predicting on. I did not provide this data. I generated new data from Timur's correlation. After training the model, I generated new data. I made the model predict on that data. I take that permeability, predictive permeability. I compared it with what Timur's correlation was saying, and those were very close to each other. So this is when I realized that, yes, there is something good about machine learning. If you provide the right, the best thing about this was the data was very clean. You can see the distributions are perfectly normal and there's no noise in this data. Everything is ideal, which is rarely the case in real life. That is something that you have to learn. If you learn the right tricks to make the data ready to be used in machine learning, the better the data, you can fairly trust your machine learning model, just like I have done in this case. So finally, the machine learning model has understood a correlation that it had no idea about. Okay, just because the data was good and I trained the right model on it. So these are the few techniques that you might have to learn as you go on. But the good thing is it does happen, which we have seen right now. Okay, so you might be inaccurate because of the data having a lot of noise. You might be inaccurate because the algorithm you are using is not correct. You might be inaccurate because uh, there is some semantic problem with coconut water is sometimes negative, which is not possible. So you might have to do all that processing and all, and you might have to correct all of them, right? And finally, once you do, you can see that the machine does understand the physics. So just imagine, guys, if you are seeing this example which is working, why not would this work in any other field? If you have a field data, you have lakhs of samples of porosity permeability data, why use old correlations? Why not use your own correlation base? Why not build a machine learning model on the same correlation, some same data? Why not just forget the old correlations, try to build your own correlations from the data itself? And with that motivation, let's conclude today's session and finally go for questions and answers. And I have also curated a list of this is just a few examples from what I have done. So to learn all these, they are all located in my GitHub. So if you want to learn all these things, you want hands-on experience with them, you can just replicate these things. You might have to spend 1 month on learning Python, maybe, but once you do that, you are ready to be using all these repositories. So that's it. I think we can now do some questions and answers.
Thank you very much for the presentation. It's like, you should maybe apply for a professor job at a university. It would really be good.
Yeah, I wish they hire young professors. Need to white my hair first.
Does anybody have any questions? They can just unmute themselves and ask. Fikri, please go on.
Yeah, thank you for the very insightful presentation. Yeah, I have questions regarding the model in machine learning. So basically in geology, the model is referred to the, for example, like the 3D models of the reservoir, for example. And here in machine learning, you refer the model as a various kind of values of a particular parameter. I just want to have more insights about that. Like, what is the model in machine learning referred to?
Yeah. That's a good question. So, when you learn mathematics, right? When you see something, so for example, suppose I draw x-axis and y-axis, and I draw a few points x comma y, x1 y1, x2 y2, x3 y3. You can visualize that, right? I draw a few points on the graph paper, and I ask you to draw the best line that you can, or best curve, whatever you can, to connect all these dots. And if these dots that your brain sees that, hey, these dots are very linear, you would draw a straight line right away, right? This straight line that you just drew, that's your model. And if you know mathematics, you would realize that this model has an equation, which is y equals to mx plus c. And your brain has already figured out what is m and what is c. That's why you could draw the straight line so accurately, because your brain has already figured out that, hey, this should be the intercept, this should be the slope, and that's how the line would correct all these. Similarly, these x comma y points, if you provide to the machine would again fit the same thing by realizing that correct intercept and correct slope. So the model is always some sort of mathematical equation that the machine fits in depending on the data. The good thing is, with the trend coming in about artificial neural networks and all, there is no limit to the kind of equation that the machine has to fit. So if you know decline curve models, they are limited that this is the kind of equation that you have to fit, otherwise nothing else you can do. But machine learning brings in the flexibility that there is no foundation on any kind of math, any kind of equation that the machine wants to fit. If the linear equation is not the best model, then you can fit a parabolic equation. If that is not the best model, you can use non-linear models. If it's too complex, you can use a neural network. So that's how model is. A model, for summarize, a model can be any math equation that can be of any form. I hope that cleared.
Oh yes, thank you so much. And it gives me more questions, I guess, because of your answer. So, is there any quantitative approach so you can say confidently that your model is correct or be trusted?
Right, definitely. So, like I told you, in the model that I created, finally, when I was confirming in the last Timur's correlation model that I was looking at, I only trained my machine learning model on 80% of the data. I have, let's say, 1,000 rows of data. I would use only 800 rows for my machine learning training. Okay. And the remaining 200 rows, I know the X and Y for them also, but I would use them for testing my model. So suppose I have created five parallel models. I would test them on the unseen data set, because unseen data is the real world data. You would use the model in real world applications where you don't know the actual answer, right? So the performance of the model on the unseen data, the test data, that is that you can use for comparison. The accuracy of the model on the unseen data, suppose one model gives an accuracy of 87%, the other gives 90%, the third model gives let's say 70%, then you know which of the model can be picked. So there are a lot of approaches that you can pick for picking up the right model. Visualizations also help. I can visualize, even if my linear model is providing right accuracy and my mathematics understanding tells me that the actual relation must be non-linear, then I would rather use the non-linear model. So a lot of things come in. Domain knowledge also comes in. Math understanding comes in. A lot of things come in to finally evaluate. Varies from a particular example to other. But this test data comparison, it always helps.
Okay, yeah, thank you so much. That's nice.
You're welcome.
Anyone
Any
else?
other questions? Any other questions about even from not this topic? I mean, any topic, drifting from this topic, whatever you want to ask. Don't hesitate.
Dennis, please go on.
Hello, thank you for your presentation. I have a more general question.
Yeah.
I would like to know if maybe you have tried it yourself. How possible is it to use the techniques that we have already learned in machine learning to move from one field into another? Let's say you learn some machine learning working on petroleum, and then you want to do maybe mineral exploration. How possible is it to use those techniques there?
Good question. So if your fundamental understanding, because I told you that the central machine learning models, they are all math in a way, right?
Yes.
They are not something else. So like I was giving the example to Zen, I was telling him that, hey, if I give you X comma Y, replace that X comma Y with porosity comma permeability, that becomes a petroleum example. If I replace them with height comma weight, that becomes a biological example. If I replace them with diameter comma effectiveness of a drug, that becomes a healthcare example. But the central model remains the straight line model, right? The math that you are using is the same. So you are using the same machine learning model across industries. So that's the good thing. The skills that you learn for any industry, if you are focused enough on the skill that you are learning, if you know how to do something in Python, if you know the math behind it, you would never be hesitating in applying it to other industries. One thing definitely that you might be challenged at is data cleaning part. For example, I know that porosity greater than 47.6 is not possible, right? 0.476 is not possible. But if I was not a petroleum engineer and I was working on the same example as a healthcare engineer, I was working on a petroleum example, I would not exclude the 47.6. So that's where domain knowledge is very important. You will have to consult a team of subject matter experts, which will be there in every data science team. You will have to use a lot of suggestions from them to make sure the data processing is as at par with the domain knowledge. So the math does not change, just that a few fundamentals, they need to be aligned with the domain you're working on.
Okay, thank you.
You're welcome.
Okay. Anybody else have any questions? Fikri. Oh.
Sorry for asking so many questions, but will be more, not related to the topics of the presentation. So as far as I know, your position is in Accenture, and you are a data analyst, while your background is petroleum engineering. What are the hard skills that must be learned to become a data analyst with a quite contrasting educational background, especially as petroleum engineering? Thank you.
And now that we have started petroleum from scratch, nothing is now difficult. We are trying to convey the workflow to everyone. The difficult part that I felt 2-3 years back when I started with this was there was no clear guideline on the path that that should be followed. But now I've realized that you learn, step one is to learn Python, then you learn NumPy and Pandas, and then you learn Matplotlib, and then you do some projects from textbooks or projects from the other websites, and then you publish these things on LinkedIn and so on, and you become very, very good at data science and data machine learning and all. So this workflow was so simple, but yet no one was telling us that, right? So that's something that was the difficult part. I will never say that learning these skills are difficult at all. If you are passionate enough about mathematics, machine learning will not be a challenge. In fact, you would love that challenge. If you love mathematics, if you want to solve some equations on pen and paper and then code the same thing on Python, if you go to my GitHub repository, you would see that I've actually coded a lot of mathematical models from scratch without using any Python packages. But then I do the same thing using a Python package, and I realize how much time I can save. So nothing is difficult, but the only difficult part is staying consistent and motivated, which is something that is something that I have rarely seen. People just drift away, and that's something. But people who have not drifted away, I've seen great results on them. So I hope you got the answer.
Yes, thank you. Now it's all clear.
Yep.
Thank you very much. I think we are done for the presentation. And if anybody is interested, and we would like to request everybody to switch on the camera so that maybe we can take a group photo and put it on the website if you are interested. So yeah.
I think this profile picture looks better than I do right now. So I think let that be. I'll share my LinkedIn as someone has asked.
So do we have the photo, Aditya?
No, you do it, please.
Oh, okay, okay.
Yeah.
Okay, 1, 2, 3. All right. Thank you.
Thank you very much. And Divyanshu, we would actually like to give a certificate to you, but yeah, we would do it like I would personally send it to you afterwards. After our faculty advisor signs it, then I could give it to you. Okay.
No worries, sure.
Yeah. Thank you very much again for your presentation. Yes, it was really, really helpful.
I'm glad. Thank you. Best of luck,
Thank you.
everyone. Bye.
Bye.
Bye.